This is question 6, and this is one where it involves finding the shortest distance, which is something that a few people struggled with. So let's go through this and see how we do that. So again, pretty standard start. We have ship A moving with constant velocity, and we're told what the initial position is. So R is just equal to 13I plus 5J plus 3I minus 10J times by T. Get all your I's together. 3 plus 3Ti plus 5 minus 10Tj. Done. That's all that one is asking. This is one that people often overthink as if there must be more to it, but it's just asking for the position vector. Okay, we've got another ship moving. Immediately I'm thinking, okay, I write this in terms of I's and J's. That's its initial position. And then this is its velocity. So this is 3 plus 15Ti plus 14T minus 5J. Okay, that's my position vector for B. And again, this should be pretty well ingrained into you now. If you're going from A to B, to get that vector, you subtract A from B. So A to B is RB minus RA, which will be 3 plus 15T minus 13 plus 3Ti. So that's my I components, subtract my I components, plus my J components, subtract my J components. And I can do that now. That's 15T minus 3T is 12T. 3 minus 13 is minus 10, and that's I. And then 14 plus 10T is 24T. Minus 5 is minus 10T, minus 10, and that's my J's. So you can see there, I've got exactly what it asked for. My recommendation, anytime that you're producing a vector, is getting all your I's and your J's separate. You're going to want to deal with them in I and J form. So do that as soon as you find the vector, and then just use that vector each time you go, you have to. Okay, so now we have A to B, and we're told that the two ships do not change course, so there's no acceleration, constant velocity. Find the shortest distance between the two ships. When you see distance, you should think Pythagoras when it comes to vectors. We know A to B is something like this. That's A to B. And we know not what this line actually is, but we know what the across components and what the up components are. The across components are the I's, which is 12T minus 10. The up components are the J's, which is 24T minus 10, like that. And so to find the distance, all we have to do is Pythagoras. This missing side here is that side squared plus that side squared. Or in other words, the I component squared plus the J component squared. Well, when I say that's the distance, that's obviously the distance squared. So the distance of A to B is equal to the square root, but I don't want to do the square root, so I'm just going to write the distance squared of 12T minus 10 squared plus 24T minus 10 squared. Now, I recommend writing squared here so you don't have to write a square root every time, but let's not forget that this is the distance squared. That will become important later. So, the shortest distance between the two ships. Well, I found an expression for the distance. Let's simplify this out. So that's 144T squared minus 10. That's minus 240T t plus 100 plus, I don't know what 24 squared is. 24 squared is 576 t squared minus 480t plus 100. And if I add all of this up, I get 720 t squared minus 720 t plus 200. Okay, so this is my expression for the distance. Now, a couple of things to note here. This is an expression for the distance squared, which means that it can't be negative. And we also know that the distance can't be negative anyway, right? That doesn't make any sense. So what that means is that it does have a minimum value. If it can't be negative, then the minimum value is at least 0. So what do we do here? Well, we've got that this is the distance. If we knew what the minimum value of this expression was, then we could work out the minimum value for the distance as well. This is a quadratic expression, and you should know from your knowledge of quadratics that quadratics do have a minimum, and we have ways to find that. The easiest way, to be honest, is differentiation. I don't know if you'll have all done differentiation at this point, but if you do know how to differentiate, then that's probably the best way of doing it. So if I differentiate with respect to t, what I will get is 720 t. No, what? Sorry. I'll get 1440 t minus 720. And I want to set this equal to 0 to find my minimum, my turning point. And this gives me t equals 1/2. That's one way of doing it. The other way is by completing the square, which is a lot less convenient, but also possible. We get t squared minus t in here. We'll just leave the 200 outside. And then I could complete the square in here, minus a half, minus a quarter, plus 200. What's a quarter of 720? 180. So this is, this is t minus a half squared, minus 180 plus, wait, what? What's going on? Plus, oh yeah, no, that works. So this way actually does directly give me what my minimum value is. This is when t equals a half. It tells me directly that ab squared, remember that squared is important, is equal to 20. That's my minimum value for the distance. So my minimum, sorry, for the distance squared. So my minimum value for the distance will be 2√5 or √20. For this method here, for the differentiation way, I do have to sub back in. So I would have to say ab squared equals 720 times by a half squared minus 720 times by a half plus 200. That gives me equals 20. That gives me that ab equals √20, which is 2√5. So actually, in some ways, I guess completing the square is kind of easier there. Depends how confident you are algebraically. Either way, none of those two methods should actually be hard to you all. So that's how to get the shortest distance. We are finding just an expression first of all, without actually trying to figure anything out. An expression for the distance between the two things based on the Pythagoras that we get from the in-between vector. That gives me an expression which I then minimize either by differentiating or by completing the square. And then I use that to find my minimum distance. Find the bearing of ship B from ship A when the ships are closest. When the ships are closest, we know that t equals 1/2, and then we just need to find what that vector is. So that would be 12 times a half minus 10i plus 24 times a half minus 10j. which is equal to 6 minus 10 is minus 4i, and then 12 minus 10 is plus 2j. So that gives me my vector of a to b. So if a is here, then I'm actually 1, 2, 3, 4, 1, 2. So if a is here, then b is here, and that is how you get from A to B. I want the bearing of ship B from ship A, which means I'm starting at ship A, and I want that angle all the way around. Now, that distance is 2, that distance is 4. How do I get this bearing all the way around? Well, there are different ways of doing it, right? There are different angles I could calculate. I could calculate that angle inside there and add that onto 270, but in my opinion, the easiest way, as this one looks, is going to be to find that angle there and subtract that away from 360. So the way that I find that angle there is I'll do tan inverse of opposite, which is 4, over adjacent, which is 2. And so tan inverse of 2 is 63.4. And then I'll do 360 minus 63.4, which is 296.6 degrees. Done. So again, for anything to do with bearings, my recommendation is always try and draw a relatively accurate diagram, especially once you've done something, you found a time, and you've produced yourself a new vector. Draw that vector out and see what happens then, because these bearing questions, you're going to find an angle with a triangle, but then it's what you do with that angle that actually decides whether you get the right answer or not. Let's just double check that is right. Yeah, that is right. Okay, cool. There you go.